So in this video, the goal is going to be to use inductive reasoning to develop the general power rule. And what we want in particular is we want to be able to find a pattern for the derivatives of the functions f of x of the form x to the a, where a is any non-zero real number. We don't want to look at the case where a is equal to 0, or in other words, x is equal to 0, because if x itself isn't 0, then x to the 0 is equal to 1, which is just a constant function. So we're going to look at functions f of x equals x to the a, where a can be any real number other than 0. Our tool for finding derivatives right now is the difference quotient. So we know that the derivative of f can be found by taking the limit as h goes to 0 of f of x plus h minus f of x all over h. And when we're using the difference quotient and taking the limit as h goes to 0 to find a derivative, we've seen from previous homeworks that the algebra can get messy, and we don't want to have to use the definition of the derivative every time in order to find a derivative. So the goal is to find patterns or tools for finding derivatives that allow us to find a derivative without having to use the difference quotient every time. So one technique that a student can use to try to establish something is to do a few examples and then see if there's a pattern and then generalize from that pattern. That process is called inductive reasoning. That process doesn't prove something's true, but it can give evidence to us that something might be true. So what I've done is done four functions that have the form x to the a. 1 over x, which is the same as x to the negative first power. So in this case, a is equal to negative 1. The function x, which is the same as x to the first, so the case where the a is equal to 1, x squared, or the case when a equals 2, and x cubed, the case when a equals 3. And for each of these four cases, I've applied the difference quotient to them and the definition of the derivative. So I've taken the limit as h goes to 0 of the difference quotient for each of these functions. I'm not going to talk through the algebra here. That's something that you can do for yourself, and you've been doing in the homework that's led up to this point. What we want to do is look at the result in each case and see if we can identify a pattern. So here, this first one, I want to recognize that negative 1 over x squared can be rewritten as negative 1 times x to the negative 2. We can bring that x squared up into the numerator position as long as we write the opposite of whatever exponent is in the denominator position. So I can rewrite it like this. 1 can be rewritten as 1 times x to the 0. X to the 0 is equal to 1 as long as x itself isn't 0. Here I have 2x, which can be rewritten as 2x to the first, and then we have a 3x squared. And what we want to notice in each case is 1, the first thing to notice is that the number that was in the exponent position, a equal 3, a equal 2, a equal 1, a equal negative 1, the number in the exponent position to begin with in each case is wound up as the coefficient on x. So that the exponent was negative 1, now there's a negative 1 in front of the x. The exponent was 1, now there's a 1 in front of the result. The exponent was 2, now there's a 2 in front of the x. The exponent was 3, now there's a 3 in front of the x. And then the next thing to notice is that the number that's now in the exponent position is just the number that was in the exponent position to begin with, decreased by 1. So 2 is 3 minus 1. 1 is just 2 minus 1. 0 is just 1 minus 1. And negative 2 is just negative 1 minus 1. So from this, we could make a guess. We could say, hey, if I had a function f of x equals x to the a, and I decided to take the derivative of it by using the difference quotient, so I took d dx. d dx means take the derivative of the thing. I took d dx, and in each case, what did we wind up with? Well, we wound up with the derivative f prime of x equaling Well, it looks like the number that was in the exponent position came down in front of x, and the number in the exponent position on the result is just the original exponent decreased by 1. So based on the pattern, this is what we would guess the derivative of x to the a is. A times x to the a minus 1. And indeed, that's the case. So the next slide just summarizes that result. If you have a function f of x equals x to the a, and you want to take the derivative of it, so you're taking d dx of x to the a, just bring the number in the exponent position down in front and decrease the number in the exponent position by 1, and you have the derivative. So again, we used inductive reasoning to come up with this result. It doesn't prove that it's true. It gives us some evidence that it's true. But later in the semester, when we have additional tools in our pocket, we will establish this more concretely. And in the next video, I'll also, for those who are interested, I'll look at a slightly different way of justifying it.